Hello, my name is Frank Kane, and I'm the owner of Sundog Education. You're joining over 500,000 people around the world who have learned machine learning and big data and data science with me. And today we're going to talk about XGBoost in depth, a little bit more in depth actually than we talk about in my course even. So I hope this is helpful for you guys. We're going to do things a little bit backwards here. So normally I talk about the theory first for a while and do some slides, and then I show you an example, but I'm going to jump right into the example right now this time and get your feet wet and just show you what it can do. Then we'll come back and discuss the theory in a little bit more detail and go through the code again to understand it a little bit better. So let's just hop right over to my other monitor here. And I have a very simple Jupyter notebook here. So we're going to be talking about using XGBoost within a Python environment. Specifically, this is within Anaconda. So if you are new to this whole field, kind of step one is to go install Anaconda on your system, which will give you the scientific Python environment that you need to do machine learning and run things like XGBoost on your own system. Now, XGBoost doesn't usually come pre-installed with these things. So the first thing you need to do is actually install it, which is super easy. You just go to your terminal or your command prompt or your Anaconda prompt, whatever your operating system has, and just type in pip install XGBoost and you're done. That's all there is to it. XGBoost is really cool. It's one of the most powerful machine learning algorithms out there, and as you will see, it's very easy to use. I'm going to talk about the dataset a little bit more later, but again, I just want to dive in and get you results as soon as possible here. So we're going to be using the iris dataset within this specific example, and that's a very common sort of test dataset that people use in these sorts of examples. What it is a dataset of various measurements of iris flowers, and it turns out that there are two different kinds of petals in an iris. One is called the petal, which is sort of the outer petals of it, and there's the sepal, which is sort of this underneath petal that supports the outer petals. And by taking these measurements of the length and width of each petal and sepal, our challenge is to predict what species of iris we're talking about here. So that's what this data set's all about. First thing we do is load it up, and that's built into scikit-learn, which is a popular library for doing machine learning within Python. So we just say from scikit-learn datasets import load iris. All we do is load up that dataset. We can preload the number of samples and the number of features within that dataset here. Features is just, what are the attributes that we're trying to use to predict that species on. In this case, it's 4. That would be the petal length and width and the sepal length and width. And we just print that out to make sure that it makes sense. Sure enough, we have 150 different samples in this data set. It's pretty small. And 4 features, like we said, the width and length of the petal and sepal. And the target names are what we're trying to predict. So it can be one of 3 species of iris: setosa, versicolor, or virginica. Now, obviously, in the real world, you're going to be spending a lot more time preparing your data, cleaning your data, doing feature engineering. We're not going to get into that in this lecture here because that's a much bigger topic. We do go into more depth on my larger course on that, on machine learning and data science. But anyway, we're going to start off by importing this in, splitting it up into a train test split. That's what's going on here. So basically, we're going to take, in this case, 20% of our data and reserve it for testing. And we're going to take the remaining 80% and use that to actually train our XGBoost model. And that way, we can make sure that we can evaluate the performance of this model on data that it's never seen before. We're going to talk about that in a lot more depth shortly. Finally, we get into the guts of XGBoost, and we say we're going to import XGBoost itself as XGB, and we need to set up what's called a D matrix structure within it. D matrix is basically a data structure associated with XGBoost. XGBoost is not just made for scikit-learn, it's not just made for Python, it has its own API basically. And its API expects something called a D matrix for its training data and its testing data. So that's what we're creating here. Fortunately, it's very easy to do here. We just say xgb.dmatrix, pass in the training data and the testing data with the appropriate labels that we want to use to train that with as well. Again, if you're new to machine learning, we're going to dive into this in more depth shortly. Let's go ahead and run these before we forget. So let's go ahead and load up this first block. I'm just hitting Shift-Enter to execute that, and that will load up our data set. And now I'm going to click on this. That's going to perform the splitting up of that data into training and test data. And we will run this to actually convert that to the format that XGBoost expects. All right, next we need to set up some parameters. And we're going to talk about hyperparameter tuning later on. These are basically all the knobs and dials that you use to adjust how XGBoost works. How deep do you want the trees to get? How fast do you want the learning rate to be? What objective function do you want to use to actually measure how good it's doing? How many classes do we have that we're predicting here? In this case, it's 3. Those 3 different species of iris that we're trying to predict. And how many epochs do you run? How many iterations do you want to actually go through to try to converge on the best model? So let's go ahead and set those up. And now we can just do the training with one line of code. And That's kind of the dirty little secret of machine learning. Well, one of many, actually. It's really, really easy to do these days. In pretty much any model, you can just say, you can take your model and say train, pass it into your training data and any hyperparameters that you want, and it just does it. So that's all that's going on here. We're actually building up an XGBoost model here, feeding it in that training data of iris data and the parameters that we gave it. Those are those parameters and the number of epochs, so 10 iterations there. And that's just going to go ahead and make that trained model based on our training data. And as you can see, that happened really, really quick. And now to make a prediction, that's also very easy. One line of code. We just say model.predict. So we're taking that trained XGBoost model and feeding in that 20% of data that it hasn't seen before, that we held aside while training the model to see if it can successfully predict the species of an iris just based on the measurements of its petals and sepals. So let's go ahead and kick that off. So now we've stored those predictions in this variable called predictions, and we can print them out, see what they look like. And those are basically all of the species predictions that it made for that test data that we set aside. This is the model predicting what species of iris we have just based on the measurements of that iris on data that's never seen before. And these 0, 1s, and 2s represent different species of iris. Doesn't really mean much looking at it though, so we need to actually measure how accurate that is. Again, that's very easy to do. Scikit-learn has a accuracy score function that can do that for you automatically. We just pass in y-test, which is basically the data set of the correct answers that we know, and the predictions, which are the predicted answers that the XGBoost algorithm gave us. Let's run that. And amazingly, the accuracy is 1.0. That means that it is 100% correct. You don't see that very often, guys, and that's very much a reflection of just how good XGBoost is. Granted, it's a small data set, so it's a little bit easier to get 100% accuracy on a data set that's this small and easy to work with. In the real world, probably won't see that. But even by small data set standards, that's pretty impressive. So there you go. XGBoost in a nutshell. And we didn't even spend any time trying to optimize the parameters of it or anything. It just kind of worked out of the box. So pretty cool stuff. XGBoost is amazing. So you've seen it in action. Let's spend some time actually talking more about the theory now and what's going on here. Now, I'm going to assume that you're relatively new to machine learning, so we're going to take some time and step back and talk about things like what is a decision tree, what does boosting mean, what are ensemble methods, what does it mean to do train test or k-fold cross-validation. So, if you are more experienced in these areas, feel free to just skip ahead through those sections. I won't be offended. But we're also going to talk about XGBoost itself in some detail as well. So let's pull up my slide deck here. All right. So yeah, let's talk about XGBoost in a little bit more depth. XGBoost stands for Extreme Gradient Boosted Trees. And it's what we called an ensemble method. So basically it's taking a whole ensemble of decision trees and using a boosting method to boost the attributes that led to misclassifications of the previous tree. So basically, it looks at a tree that it's built to represent our model of predicting stuff for our data. It tries to find the things that it got wrong and focuses its energy, if you will, on sort of improving the performance on the stuff that it got wrong. And it just keeps building upon that iteratively until we get a model that works really well. And it is a really amazing algorithm. I mean, you hear a lot about deep learning these days and, neural networks and all that stuff, but XGBoost can definitely give deep learning a run for its money. It routinely wins Kaggle competitions, even doing better than deep learning in a lot of cases. And as you could see from that little simple example we had, its performance was really, really good. And it's also very easy to use, as you just saw. It's very fast, as you just saw. So it's usually a really good algorithm to start with if you're going to be trying to solve some sort of general machine learning problem. People kind of use deep learning these days as a jack of all trades, sort of like a hammer to fit every nail. But XGBoost can often do a lot better, and it's often even easier to use than deep learning. So let's back up a little bit. What do we mean by a tree in the first place? So if you're familiar with decision trees, skip ahead a few minutes. I won't be offended. But decision trees are kind of like a flowchart, right? So you can actually construct a flowchart to guide you toward a decision as to what sort of a classification you want to give to a given problem in machine learning. This is called a decision tree. It's a form of supervised learning, which means that it actually you train it with a set of the known correct answers, so it can actually compare its predictions to the right answers as you go through the training stage. But basically, you just give it some sample data and the resulting classifications that you know are correct, and out comes a tree like this. So in this little simple example that we're looking at here, we're trying to figure out, should we go outside and play today? And we basically have two categories that we can come up with, either play or don't play. And we have various features about the weather. Is it sunny? Is it overcast? Is it raining? Is it humid? Is it windy? So the decision tree tries to figure out what's the best way to organize these different decision points as to whether I should play or not play. So is it going to be sunny, overcast, or is it going to rain? Based on the thresholds that I have there, I might have different logic as to which branch I take in this tree. And furthermore, once I figure out that it's sunny, well, I figure, well, is it too humid? Right here in Florida, it sure is. And I can say, well, if it's less than 70% humid, go ahead and play. Otherwise, stay indoors. And the beauty of it is that a decision tree algorithm can sort of optimize automatically what decisions to make, what thresholds to have, and what order to organize these things in, and how deep to go. And that's kind of the magic of the algorithm. It does it by doing something called minimizing entropy as it goes down. So there is sort of a way of doing it that makes sense mathematically. I don't want to get too much into the guts of that right now. If you want to learn more about decision trees, my larger course goes into it in a little bit more depth. But as an example, let's look at a little example here. Let's say you want to build a system to filter out resumes based on historical hiring data. This is kind of a scary example. It kind of implies that you could actually decide whether or not somebody gets a job without a human being in the loop, which is, obviously cause for concern. If you have, well, I don't want to get into the ethics of machine learning, but you can get into these situations where you're baking in the biases of humans into your training data, and you just end up training your algorithm to have those same biases, which is bad, but I'm not going to go there right now. Let's just imagine, though, that we have a database of some important attributes of job candidates, and we know ahead of time which ones were hired and which ones weren't, or maybe even better, which ones actually lasted, ended up being successful at your company. So you could train a decision tree on that data and arrive at this system that would predict whether a candidate gets hired based on attributes about that person. For example, we could look at how many years of experience they have. Are they currently employed? How many previous employers do they have? What's their level of education? How good was their school? Do they do an internship? And based on these features, we call these various attributes features in the world of machine learning, we could try to predict the label of whether or not they were hired. So, we just have some totally fabricated data here. And if we actually punch that into a simple decision tree in scikit-learn, we can end up with something like this. And it actually starts at the top of, did you do an internship? It turns out that's actually a really good predictor as to whether or not you're going to be successful in the real world. And in the little fake data set that I gave it, anyone that had an internship ended up getting hired. So we can just stop right there in that case. But if not, we can look at their current employment status. If they're not currently employed, then we want to dive a little bit deeper. How many previous employers did you have? And, if you're failing that test as well, we can take a look at the quality of the school that you went to as a last resort for deciding whether or not to hire this individual. This is a pretty simple decision tree because it's just linear. There's not a bunch of different branches you can take really, but the algorithm can figure out automatically how that actually comes together. How does it work? Let's go into a little bit more detail on that. So basically at each step while we're training the decision tree, we find the attributes that we can use to partition the data set to minimize the entropy of the data at the next step. And entropy is basically a measure of disorder. It basically gets down to how uncertain am I about the result at that point in the tree. And there's a fancy term for that algorithm. It's called ID3. It's what's called a greedy algorithm. So as it goes down the tree, it just picks the decision that reduces the entropy the most at that stage. Basically, it's looking at what decision point can I pick that will give me the most clarity as to whether or not the classification I want is correct. And that might not necessarily result in the most optimal tree, but it works. And that's how it generally works. Now, we can take that and kick it up a notch. Instead of just having one decision tree, why not have many decision trees and have them all kind of like contribute toward the final result? That's what's called a random forest. The problem we're trying to get around is that decision trees are very susceptible to overfitting, and we're going to talk about what that means in a moment. So to fight that, we can actually create many decision trees and have them all vote on the final classification. And we do that by just randomly resampling the input data for each tree and just, letting them all have a go at it and see what they all converge on. The fancy term for that is bootstrap aggregating or bagging. And it's just as simple as it sounds. We just sort of like mix up the parameters going into each tree or the data that it sees, and we let them all vote on the final result. And this prevents overfitting by not putting all of our eggs in one model's basket, basically. We're letting multiple models be built on little variations of the problem and letting them all vote on the best algorithm. So that way, we kind of mix things up a little bit more and we get a more robust result out of the model. What do we mean by ensemble learning? Let's go into a little bit more depth about that because XGBoost is fundamentally an ensemble approach. So random forest, like we just talked about, is just one example of ensemble learning, but at a higher level, it just means that we're using multiple models to try and solve a problem, and we let them all vote on the results in some manner. And there are several different flavors of ensemble learning as well. So the random forest we just looked at uses bagging, bootstrap aggregating. The idea there is that we use many models built by training on randomly drawn subsets of the data. So in bagging, we're just creating a bunch of different models using different samples of the data and letting them all vote on a final result. That's bagging. That's not what XGBoost does. XGBoost does boosting. It's in the name, right? XGBoost. So boosting is an alternate technique that is arguably even better, where each subsequent model in our iteration in the ensemble boosts the attributes that address the data that were misclassified by the previous model. So basically, we take a tree, we try to figure out which attributes actually generated the wrong answers, and we give more weight to those on the next iteration. So we try to converge on the problem points of that model and really focus on getting that better at each iteration of the model. So that's boosting in a nutshell. And that's the basic idea behind XGBoost. There are some other techniques in ensemble learning as well. A bucket of models. Basically, you train several models using training data and pick the one that works the best. Or stacking, where you just have multiple models running at once. They can be completely different models using completely different algorithms, and you just combine all the results together. If you remember the Netflix prize, where they had $1 million prize for improving their movie recommendation system, that was actually the approach that worked the best for that one. Let's get back to XGBoost. So XGBoost is not just boosting, it's regularized boosting. And as we talked about, that prevents overfitting because we have this ensemble method where we have many different trees contributing to the final result. And that means that we avoid sort of, again, putting our eggs in one basket and potentially overfitting to a data set that was given to one model. And we'll talk about overfitting a little bit more in a moment here. Another nice thing about XGBoost is that it can handle missing values automatically. So in the real world, you're probably not going to have perfect data sets. If this were a real data set for iris flowers, there'd probably be a few cases where you didn't have measurements for the length or the width of a petal or a sepal in some cases. XGBoost can handle that for you automatically, so that makes life a lot easier because the life of a data scientist, the life of a machine learning engineer is often spent just cleaning the data they have. So XGBoost removes some of that pain from you. It's also built to do parallel processing, and therefore it's very efficient. So it can actually run these trees in parallel on the various cores on your CPU, or, in theory across different machines. But generally speaking, we're talking about different cores on one CPU. It can also do cross-validation at each iteration, and we're going to talk about cross-validation next and how that means. And by basically checking how good our results are at each step, that enables things like early stopping. So we can say, okay, I've been iterating on this thing and boosting over this many different tree models. At this point, the result's good enough. I'm just going to stop. And that's an important optimization to have, especially given how expensive machine learning hardware is, both in terms of money and energy usage as well. So it can enable early stopping and also find the optimal number of iterations. Basically, it knows when to stop, right? So that saves you a lot of wasted effort. It can also do incremental training, but that means we can start training a model. And as we get new data coming in over time, we can refine that model with that new data that we're seeing. So if we're getting more and more data on iris flowers, for example, or more and more data on who was hired and who wasn't, we can feed that in on top of the model that we have and just keep making that XGBoost model better and better as we collect more data. You don't have to start from scratch each time. So that's also a really nice feature of it. You can also plug in your own optimization objectives, but the ones that are built in are usually good. But if you are trying to optimize for something very specific, that's not just accuracy or something more easily measured like that, it gives you that flexibility. And it also has a feature called tree pruning. That means that it's just trying to optimize the shape of that tree, if you will. Generally, this results in deeper trees, but the trees that are more optimized. So like we talked about before, sometimes the way that decision tree training works, you end up with trees that work well but aren't necessarily optimized. XGBoost addresses that problem through tree pruning, and we actually do get optimized trees that might be a little bit deeper than you might expect, but they are pretty optimal. Let's back up a little bit. So we talked about early stopping and how by evaluating how good the boosting model is at each iteration, we can figure out at what point it's good enough. So how do we know how well this model is doing? And if you're familiar with the concepts of train test and cross-validation, skip ahead a few minutes. It's cool, I won't be offended. But let's say that we have a set of training data that includes the value that you're trying to predict, like we do with our iris data. So we don't have to guess if our resulting model is good or not. We can actually take those known answers, if you will, and compare how well our model does at predicting them. And the trick that we do here is by splitting it up. We have a training data set and a testing data set. The idea is to only train the model on the training data, and we hold out that test data to see how well that model does on predicting classifications or values, whatever it is, on data that it's never seen before. If you were training your model on all of your data, that's cheating, right? Like you've basically given your model the answers ahead of time. So it wouldn't really make sense to train your model on a data set that includes your test data. You want to reserve that off to the side and use that just to evaluate your model. And then you can measure the accuracy of how well your model does at predicting the known correct answers in your test set. There are various metrics for doing that, like R-squared. And we just compare it, we just look at how good it is at that point. And we use that to figure out, is my model getting better or worse as I sort of tune the parameters on it. Now, in practice, we end up with this thing called overfitting that we can run into. So the danger here in train test is that you can end up sort of overfitting to these sort of random variations in the data that don't really have anything to do with the intrinsic values of the data itself. So imagine that we're trying to predict whether a dot should be red or blue based on, some attributes associated with each dot. Maybe each dot represents the height and weight of a person or something. I don't know. But the risk here is that you might end up with a model that does this like crazy curvy line to try to like get every answer right. So the accuracy of this crazy curvy model would be 100% because it's really going out of its way to make sure that, every answer that you gave it in the training data is going to be the right one. This is called overfitting, right? So obviously this isn't representing anything real. This would not generalize well to other data because our model is basically overfitting to the training data that we gave it. A better model would be a simpler one that just has sort of this black curve here. That's probably more of a representation of what's going on in reality in terms of what attributes result in what classification. So train test kind of addresses that because by testing this model against data that it's never seen before, an overfitted model would not do well on that. It doesn't generalize, like we said, to data that's never seen before. So by reserving that test data, we make sure that we're measuring how well this model does on data that's never seen before. And so that will penalize it for overfitting. However, train test is not perfect either. If you have a small data set, which we do in the case of the iris data, there is a chance that your training data set and your test data set might be weird in the same way, right? So take a look at this example here on the right. Our training data set and our test data set actually have fairly similar patterns here that it can overfit to. So an overfitted model based on this training data would actually perform pretty well on this test data because just by chance, our test data has some of the same random fluctuations that our training data did as well. So overfitting can still happen when you're doing train test. So how do we get around that? With something called k-fold cross-validation. So a way to sort of further protect against overfitting is by doing this multiple times, basically. So instead of just having a single training set and a single test set, what we do is this. We take our data and we split it up into k different randomly assigned segments. And we go through each one of those segments. And in each step, we take one of those segments and reserve that as our test data, take the remaining segments and use that as our training data. And then we go through each segment and do it again. So basically we're doing train test k times, where we're taking a different segment of that data that's been assigned at random as our test data, and the remaining is the training data. So this, if you had k-fold cross-validation with 10 folds, you could do train test 10 different times, and then basically average the results of how well the accuracy was on each iteration to get a more robust measure of just how good your accuracy is. So that's what we mean by k-fold cross-validation. And in the context of XGBoost, that's how it's evaluating at each step of its training as to whether or not you're getting a good result. So it's doing cross-validation and saying, okay, in the most robust manner that I know of, how good is my model doing on the data you've given it? And if it's good enough at that point, it can say, okay, I'm done. I can early stop. Let's get back to XGBoost with all that theory behind us. So like we mentioned, if you want to install it within a Python environment, it's super simple. You just have to say pip install XGBoost and you're done. But XGBoost is not just for Python. It's actually a big standalone open source project of its own. And it has a command line interface of its own. It has a C++ interface, R, Julia, interfaces for Java virtual machines. So it's not just made for scikit-learn. You can actually use XGBoost within pretty much any application you want to, which is pretty cool. And because it is more general, it's not just for scikit-learn. It doesn't have a scikit-learn specific interface. So because of that, that's why we need to convert things to that D matrix structure, because that's what it's sort of native API is using to hold the features and label data. But as we saw already, that's very easy to do from a NumPy array within scikit-learn. It's not a big deal. It's just an extra line of code. You pass in all the parameters via a dictionary like we saw. It's very easy to use. You just call train on it, then you call predict on it, and you're done. Super easy to use. What's the challenge with XGBoost though? Well, like with any machine learning algorithm, hyperparameter tuning is kind of one of the hard parts. Feature engineering, the hardest part. Hyperparameter tuning, close second, I would say. And that's true with XGBoost as well. Sort of the dirty little secret of machine learning is that there's not always a whole lot of expertise that goes into using it. A lot of it's trial and error, right? So with XGBoost, there's a bunch of different parameters we can adjust. What booster do you want to use? There's two of them, GB tree or GB linear. What objective function do you want to use? Do you want to use softmax or softprob? What learning rate do you want to use? That basically adjusts, what are the weights used on each step as it goes through its iteration of doing boosting. That's called eta. What's the maximum depth of the tree that you want to allow? What's the minimum child weight? That's a way to control overfitting. But if you get that too high, you'll be underfitting. It's not always obvious what to set these to, right? Because a lot of times it depends on the nature of your data. And this is true of any machine learning algorithm. A lot of times you just have to guess, and that's exactly what people do. There's this process called hyperparameter tuning, and often what people do is they just set up this matrix of the parameters that they think are going to have the biggest impact on the accuracy of their model, and they just try different combinations across wide ranges of values for each parameter. And as you can imagine, that is extremely intensive in terms of computing requirements. I mean, that means you have to train your model and test it and evaluate it many times. So if you have this matrix of many different parameters and you're trying different values on each one of those parameters, that explodes really quickly. That's a big part of why training a machine learning model is as expensive as it is and uses as much energy as it does, because you're trying to converge on those hyperparameters. There are technologies out there that make it easier and simpler and faster. For example, Amazon Web Services has a hyperparameter tuning job as part of its SageMaker service that tries to do this a little bit more intelligently. It tries to figure out as you're going through the tuning process what parameters are having the biggest effect and sort of converges on them over time to make that a little bit more quick. And it has obviously the expansive hardware resources available to you on AWS. But again, it's not cheap. So lots of knobs and dials with XGBoost that you can play with. And unfortunately, getting them right is often just a matter of trial and error. But yeah, XGBoost is kind of awesome. It's almost all that you need to know for machine learning in practical terms. I mean, for any classification problem or even regression problems, it can do that as well. Regression is where we're trying to predict a numeric value as opposed to predicting a classification, like what species of flower do I have. So let's go back to the code again and go into a little bit more depth this time and see it in action. All right, so we're back at my notebook here. Let's go through this one more time, and then we'll call it good. So again, we're just using XGBoost here and showing you how easy it is. Let's restart our kernel and clear the output. Start from scratch. All right, so again, installing, just a matter of saying pip install XGBoost. Super easy. And again, we're using the iris data set. And let me pull back that slide for a moment here. So again, we have what we call petals and sepals. You can see here in this close-up of an iris that there are two different types of petals on an iris. Those outer ones are the petals, and those inner ones are the sepals, okay? So our iris data set just has 150 samples of measurements of the length and width of the petal and sepals, and it has the correct answers of what species those flowers are. So let's go ahead and hit Shift-Enter to load that up. And again, in the real world, you would not have a perfectly clean, beautiful, complete data set like this. Odds are you'd have a much bigger data set for one thing. You'd probably have missing data. You'd probably have erroneous data. You'd have outliers that made no sense. So again, pruning that data and cleaning it up is often the biggest part of the job. Our larger course goes into that in more depth. And even worse, you might have many different features to choose from. Maybe we had more than just the measurements of the petals and sepals, and we had to figure out that those were the most relevant features to actually use for predicting what species of flower this is. Maybe we also had data on what color it was, or how tall the plant was, or where it was grown. Who knows? Oftentimes you just have this sort of like flood of information that's being thrown at you in machine learning, and a big part of the job is just figuring out which of those features are the important ones for your model. That's called feature engineering. And again, we go into that in much more depth in our course. So we talked about train tests. So if you are new to that, hopefully this line will make more sense to you this time. Here we're actually just doing a straight up train test. We're not doing k-fold cross-validation. We're just going to take 20% of our data set, reserve that for testing, and we're going to train our model on the remaining 80%. So what this line is doing in more depth, train test split returns to us 4 different data sets, NumPy arrays more specifically. Now in the world of machine learning, we typically talk about the feature data as X and the label data as Y. So the label, Y, is the thing we're trying to predict. Those are the species of each flower, right? Whereas X is going to be the feature data. That's going to be the measurements of the petals and sepals. So we're going to take out the feature data, those measurements, and split that into a train test and a test set. And we're going to take the labels, basically the correct answers, and split that as well into a train test and a test set. So we have that into X train, X test, Y train, and Y test. Let's go ahead and run that block before I forget. Now we're going to load up XGBoost itself, which we already installed ahead of time. We're going to call it XGB, a shorthand, and we're just going to say XGB D-matrix to construct that D-matrix structure that XGBoost expects given the X train data. So basically here we're saying we're creating a D-matrix where the feature information is from the training data set and the label information is from the training set. So it's being passed in those features of the width and length of the petals and sepals and the correct answers so it can use that for actually optimizing the model as it goes. We'll also give it our complete test data set, which will consist of the test data that we reserved, both the feature data and again the label data. So this is again the measurements and the species for our test data set. Next we define our hyperparameters. Let's run that block before I forget. And here we just kind of like took a best guess as to some parameters from the documentation here. We're actually capping the depth of the tree to 4. The learning rate, eta, is set to 0.3. For the objective, we're using softmax. And we do have to tell it how many classes that we have. Num class is just how many different labels do we have. So we have 3 different species of iris that we're trying to predict here. So that value is 3. That one you don't have to guess about, but the other ones are basically hyperparameters that should be tuned. And like we said, the process of hyperparameter tuning can be very intensive. We also need to pick how many epochs we're going to run this over. That's another hyperparameter. How many iterations do you want to go at the most in training this model? So let's go ahead and define those parameters. And now we can actually train the model given those parameters and the number of epochs that we want to use. And that is incredibly quick, right? Granted, it's a small data set, but even so, XGBoost is really, really fast. Now we'll use that trained model to make predictions. Notice that we passed in the training data here for the model, and now we're going to pass in the test data to evaluate how well that model does in predicting things that it's never seen before. Again, really quick, let's go ahead and print those out. These are basically a list of the species predictions that it made for each sample in our test data, and then we can again go ahead and measure how accurate that prediction was. So we're going to import accuracy score from sklearn.metrics. Call the accuracy score function here, given our test data and the predicted labels. So we're giving it the known correct values here, basically from our test data and the predicted species. And we're going to compare those predicted species to the known correct ones and measure the accuracy of the model. And that came out again to a perfect 1.0. So that is XGBoost in a nutshell. Hope you guys enjoyed our sort of little delve into the world of XGBoost. Again, very simple, easy to use, and it works really, really well. Like I said, it's kind of winning a lot of Kaggle competitions lately, and it's just a matter of trying it out, getting those hyperparameters right, and pretty much all there is to it. If you do want to learn more about hyperparameter tuning and feature engineering and more in the world of machine learning and data science, do check out my course, which is presumably linked to in the description here somewhere. And yeah, again, this is Frank Kane from Sundog Education. Thanks for hanging out with me for this half hour, and I hope you learned a thing or two about XGBoost and maybe some other stuff too. Take care, guys.